Group 2 carbonates, nitrates and hydroxides all decompose if we heat them strongly enough. The metal carbonates decompose to form carbon dioxide and the metal oxide. So we have here, for example, magnesium carbonate decomposing to form magnesium oxide and CO2. The metal nitrates decompose to form the metal oxide, nitrogen oxide and oxygen. So here we have calcium nitrate breaking down to form calcium oxide, nitrogen oxide and oxygen. And finally the metal hydroxides. They break down to form the metal oxide and water, in this case strontium oxide from strontium hydroxide and H2O. We can see here that regardless of whether we're looking at carbonates, nitrates or hydroxides, as we go down the group, we are having to heat our compounds to higher and higher temperatures in order to force them to decompose. As we go down the group, these compounds are becoming more thermally stable. So barium carbonate, for example, takes considerably more energy to force it to decompose compared with, say, magnesium carbonate. The fact that each of these reactions requires an input of heat energy tells us that the overall enthalpy change of reaction is endothermic. So the enthalpy change for this reaction is endothermic. It's going to be a positive value. And logically, if we're having to put more heat in to get our compounds to decompose as we go down the group, these reactions must be becoming more endothermic. So delta RH plus 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 positive for the thermal decomposition of barium carbonate. And this is what we're really trying to explain. We want to figure out why these thermal decomposition reactions are becoming more endothermic as we go down the group. There are essentially two parts to these decomposition reactions. Firstly, we need to break up the metal carbonate or nitrate or hydroxide lattice so that we can form our metal oxide in each case. Part 2 is about decomposition of the carbonate ion to form an oxide ion and carbon dioxide in the case of the decomposition of carbonates. In the case of the metal nitrates, our nitrate ions are breaking down to form oxide ions and nitrogen oxide and oxygen. And if we're talking about the metal hydroxides, then again we're breaking down to form an oxide ion and water. Let's start by considering what's happening to the lattices. The enthalpy change when we break up an ionic lattice into its ions is called the lattice enthalpy. And theoretically, the reaction that it refers to is, well, if we take magnesium carbonate, for example, breaking down to form magnesium ions in the gaseous state and carbonate ions, also in the gaseous state. We can see here the ionic lattice of magnesium carbonate. We've got the magnesium ions and we've got the carbonate ions. Now, in the lattice, we have got millions of strong electrostatic attractions between the two. And if I want to break up this lattice, then clearly I'm going to have to put a lot of energy in. It's a highly endothermic process. In fact, in the case of breaking up magnesium carbonate, we would actually need to put in 3,123 kilojoules per mole. Now, obviously, if I'm forming a lattice from gaseous ions, so my reaction is going from ions to lattice, then that's going to be an exothermic process. Now, it turns out that the lattice enthalpies of the metal oxides, so here we've got magnesium oxide, are always more endothermic than those of the carbonate. Here's our lattice for magnesium carbonate. And the reason is simply that the oxide ion is so much smaller than the carbonate ion. So the ions can pack more closely together into the lattice, and as a result, we have got stronger electrostatic attractions, stronger ionic bonding. In other words, we can think of magnesium oxide as being more stable than magnesium carbonate. If I want to break up magnesium carbonate, as we've just seen, the lattice enthalpy is plus 3,123 kilojoules per mole. If I want to break up magnesium oxide, then the lattice enthalpy is plus 3,889 kilojoules per mole. During a thermal decomposition reaction, we are breaking up the magnesium carbonate lattice, but we are making a magnesium oxide lattice, which means we need to reverse our lattice enthalpy. We don't need to put energy in to this side of the equation. Essentially, it's exothermic. We're going to release 3,889 kilojoules per mole when we make the magnesium oxide lattice from its ions in the gaseous state. Remember that this is mainly theoretical. However, it illustrates the purpose. The difference between these two, so enthalpy of reaction, simply from going from the metal carbonate to the metal oxide, in this case of magnesium, is minus 766 kilojoules per mole. If we do a similar calculation for the other group 2 metals, i.e. we figure out the difference in lattice enthalpies for breaking up the carbonate and making the metal oxide, we find that it gets smaller as we go down the group. The difference gets smaller. So we've just seen for magnesium carbonate, it was minus 766 kilojoules per mole. But for barium carbonate turning to barium oxide, it's around about minus 596 kilojoules per mole. Now, it gets a little confusing, because on the face of it, it would seem that this reaction would be spontaneous at room temperature. After all, these are exothermic values. Metal carbonates shouldn't be stable at all, but they are. But of course, we haven't yet considered the energy it takes to break up the anion, whether it be the carbonate, the nitrate, or the hydroxide ion. Now, we can estimate the enthalpy change for each of these decomposition reactions in a couple of ways. It always comes out endothermic. We need to put in energy to break up our anion, and this seems entirely reasonable. We might think that this process is independent of the cation in the metal carbonate lattice, i.e. that whatever these values are, whether the carbonate, nitrate, hydroxide ions were in a lattice with magnesium or barium, why would that make a difference? Well, as we go down group 2, the charge density of the cations gets less. Magnesium ions have a very high charge density. That 2 plus charge is packed into a very small ionic radius. This means that magnesium ions polarize the electron density of anions they're in a lattice with, in this particular animation, the carbonate ion. This places a strain on the carbonate ion, which means it takes a little extra energy to break it down to oxide and carbon dioxide than might be expected. Barium ions, which do not have a high charge density, don't have the same effect. Let's finish by putting all this together. In order to go from the metal carbonate to the metal oxide lattice, and just that little bit there is exothermic. But as we go down the group, it becomes less exothermic. Breaking up the carbonate ion or the anion into an oxide ion and carbon dioxide is endothermic. Now, because overall each of these reactions is endothermic, that tells me that this value here is greater than the amount of energy that's released when we move from the carbonate or the nitrate or the hydroxide lattice to the oxide lattice. And we also know that in the case of magnesium carbonate, because magnesium ions have a high charge density, the carbonate ion is polarized. So moving from carbonate ion to oxide and carbon dioxide takes less energy than we might expect. The overall result is that as we go down the group, these reactions are becoming more endothermic. The thermal stability increases. Magnesium compounds are the least thermally stable, and barium compounds are the most. There's a link in the blurb below to the Crunch Chemistry website where you can find out more about the reactions and properties of Group 2 metals. And if this has been useful, then please like, share, subscribe. It makes a huge difference to a small channel like us. I look forward to seeing you next time.